and I think we can start because there will be plenty to get through. So I'm very happy to formally welcome you, Stacey, to our RSC webinar. We're very excited to hear you speak. Welcome to everybody in the audience. For those of you new to this approach, there is a purple arrow in the bottom right-hand corner of the screen, and if you click on that arrow, there is a chat button, the fourth icon out, the furthermost left. And when you click on that, you'll be able to type. So the way these webinars work is, as the speaker is presenting, feel free to type anything you like into that chat area, any questions or comments, and then there'll be a time about halfway through and a time at the end for questions and comments, and I will relay those questions to Stacey. So will you please join me in welcoming Stacey? She is University Distinguished Professor at Miami University, Ohio. Obviously extraordinarily well known in the field. She's well known for lots of things. Two of the main characteristics, I think, are assessment of student learning through development of an amazing range of concept inventories, and obviously there's lots of lovely work around meaningful learning in the laboratory and so on. She's a really great champion of our discipline and of our field, and I'm really happy and excited that she is closing off our 2018-2019 season with her lecture. And Stacey, I won't take any more of your time, but welcome and thank you very much for your time and input this evening, and we're very excited to hear what you have to say.
Oh, thank you, Michael. That's a really kind introduction. I hope I will do my best to live up to it. The format is a bit unusual. I'm usually pacing around a room and feeding off the energy of the audience, and now I'm just staring at my computer screen. So that'll be a bit unusual for me. So this is my contact information if anybody wants to get a hold of me, and off we go. So I just want to make sure everybody understands I'm not down in sunny, warm Florida. I'm actually up here in the southwest corner of Ohio in the United States. So we were actually a university when Florida still belonged to Spain. So we were Miami first. It comes from our Native American brothers and sisters who were settled here. So that's where I'm coming to you from this afternoon. So as Michael said, in our research group, we largely focus on making measures of student learning, and the work I'm going to share with you this afternoon is about how students think about the multiple representations around the corner of Johnstone's triangle and the connections that they see or don't see amongst those representations. And then the other part of our group focuses on learning in the laboratory setting, both from faculty's goals and their intended curriculum to what actually happens in setting and the contrast between students' expectations and their experiences. So I'm just going to talk about representations work today. And this work, if you're not familiar with the DEBA report that came out of the National Research Council, this is, well, it's been a long time now, 6 years ago, that this report finally came out. It calls our attention to the idea that representations are a very familiar and efficient source of communicating information for experts in the field, right? There's lots of information encoded in them. But when students or novices come to any discipline, one of their tasks is not just to learn how to manipulate the symbols and speak the vocabulary with the right grammar and syntax, but to manipulate and decode the meanings that are encoded in these representations. And so our work for some time now has been centered at trying to understand how students reason with and the meaning that they attach to these representations. So I give you here an example for just a small slice, maybe 3 lectures of the first semester of university chemistry might have these representations present in them. And, you know, as an expert, you can look at them and think, oh, I understand what's this representation is and why it's different than that. But as a student, that's really quite a lot to take in just 2 or 3 class periods. And again, this is just a fraction of their first semester in university chemistry. And so from the student's point of view, it can really be quite an onslaught as these images click by on PowerPoint slides and they wonder, am I supposed to know what that means or not know what that means? And of course, most of their decision making around that process then pays attention to what's on the assessment that the professor uses to award grades or marks in the course. And so we've centered our work there, largely around questions of what information do students think is encoded in these representations, what misunderstandings do they have about them, And how can we use these representations to get at the cognitive dissonance that students are not even aware themselves that they have? So let me give you an example of that related around the idea of the flame test here. We conducted a study and published last year this paper about students thinking about atomic emission. The flame test is an ubiquitous procedure. People perform it all the time as a demonstration. There's 50, 60, 70 different ways you can conduct a flame test for students to ooh and ah at. And when we talk to students, and I want to say all the data that I'm going to show you comes from speaking with students after they've been taught by their instructor and tested. In other words, it's as good as it's going to get. We come in 2 to 3 weeks after they've studied for their local exam, they've optimized their understanding as much as possible. What sense remains at this point? And so we ask students in our interviews to go through a POE task with us, a predict, observe, explain, and they recognize the Bunsen burner, and they often make some remark, oh, this is how fireworks work, right? They're thinking about it, and we say yes. And so could you tell what color will the flame be if we put some of this green solid in there? And the students will say green, and then they do the observation and they feel great, and we ask them why that is, and they say, well, the solid is green and the flame will be green. So then we ask them, well, let's do another one, and we give them this. Now, if I could hear you all, I'm going to ask you this question, and across the globe, I'm going to hear the word. What color do you think the students say the flame will be? You all said white. I know you did. Except that the students, when they say it, they say white, because they know that a white flame is not correct. But they quickly realize that we've set them up where green solid gave a green flame, but there's no way this white solid is going to give a white flame. And they're at a loss to explain the red flame for the lithium salt. And so then we offer them one more opportunity to do it, and we show them what we tell them is a different white solid, and we ask them what color this will be, and the students say, yes, you all just said red. That's correct what they say, because their mental model is still the color of the solid and the color of the flame need not be the same color, but that the color of the solid predicts the color of the flame. And so now when they get an orange flame for an equally crystalline white solid, they're sort of at a loss, and they turn to us in the interviews and they ask us what it is that we want to hear. And this is the point where we tell them we're really not interested in hearing what they've memorized, perhaps for a test, or them mimicking back their instructor's explanation that was given, but that we're interested in how they really think about the molecules, the atoms, the ions that are present, and what's happening to them chemically in the task that we're asking them to explain. And so we're not interested in some memorized answer, but rather how they really think. So this is an example of the task where we try to bring forward cognitive dissonance for the students to disabuse them of the idea that we're interested in some memorized answer. And I'll show you just this quote that I found when we were writing that paper, where students themselves are well aware that the faculty are well aware that students don't really understand the content of what they're doing, but they remember the oohs and ahs of the demos. And we would like, one point of our work is to aspire to be better than this, that faculty will have some data that students, in fact, don't understand the chemistry, and perhaps we ought to focus more on that. So for today, I'm going to talk to you about the work of two students who just graduated. Graduation was on Saturday. And so that's Tim Abel on the left, and I think Tim A is listed here in our participants, so I'm going to assume that's him. So if we have really hard questions, I'm going to turn the microphone over to him. And on the right, as you're looking at the picture, is Dr. Zyling Rocha Allred. And so they're off doing great things in their postdocs, and I miss them terribly, and this is their doctoral work that I'm going to share with you today. Okay, so first we're going to start with Zai's work. She's now a postdoc in Sonia Underwood's group at Florida International. But while she was here with me, we worked on developing an inventory to students thinking about probability. And why were we interested in that? Well, Park and Light published this paper in 2009 that looked at students' understanding of the quantum model of the atom. And they pointed out that probability was a particularly sticky subject for students. And the conclusion of their paper proposes that energy quantization and probability are actually threshold concepts. That if students don't have a firm grasp on what we mean about probability, that they can't apply that probabilistic thinking to a mental model of the atom. And if they don't understand what energy quantization involves, They can't, oh, I'm so sorry. Somebody somewhere is calling me on my phone and it rang in, sorry. And so they can't apply quantization and probability to their thinking about the atom. And so what do we understand about how students use these threshold ideas? So we are not, of course, the first people to delve into this. There's a huge, rich literature about students thinking of the quantum model of the atom, and there are actually been some instruments to measure this. So there's an instrument out of Tom Holmes' group that was developed to look at students' understanding of quantum, and there are 12 different topics in there. I've listed some of them, and he has data from physical chemistry students and how they reason about these ideas. And then we also delved into the cognitive psychology and mathematics education research literature about probability, because they've been thinking about that for a long time. And so rather than reinvent the wheel, we wanted to look at their models of student thinking about probability and see which ones of those transferred over to chemistry. So the questions we were interested in is, how do students reason about electron structure with regard to these two threshold concepts? And how do they use representations to explain their thinking? And we were going to provide them with representations of an energy level diagram and different representations that communicate ideas about probability of electron structure. Do they see connections between those, and how prevalent are their thinking? So these are the ideas that we set out to design. And the way we approach our work in our group is we always use a sequential mixed methods protocol. So we do the qualitative work first, and then it's followed by the quantitative work. I've only ever done it the other way around once. And so we are going to conduct semi-structured interviews to elicit the students' thinking. We video and live scribe. If you're not familiar with live scribe, it's a digital pen that has a camera at the end of it so that we can capture a pen cast of what students are saying and drawing at the same time. And so as a student, it produces this kind of a transcript. So as a student's drawing an object and they're saying, well, this touches that, or that moves over here, we can identify antecedents for those pronouns that they're using. So it's a very helpful pen cast of the student's transcript for us. And we provide them with multiple representations during their interview because we're trying to explore that cognitive dissonance that I showed you before with the flame tests. And then, of course, we code and analyze the verbal transcript as well as the video data that we're provided with. So for this particular study, we interviewed 34 people across, so general chemistry, term here in the States, I should put my SERP hat on. I know whenever I submit a paper to SERP, never to say general chemistry. That's university, first year university chemistry. And then we also interviewed 8 students who were in our junior and senior level physical chemistry course. And because I'm in a Department of Chemistry and Biochemistry, we offer that course in 2 different options. One is a traditional physical chemistry course, and the other is set in biophysical. And so we have those 2 samples as well. And as I mentioned earlier, all of our data is collected post-instruction, post-assessment within the course. And so here's a look at the interview for this particular research project. We often start out, before we introduce any representations or try to generate any cognitive dissonance on the part of our interviewees, by exploring their prior knowledge. What is it that they know about these ideas before they come into the interview? And then in the next phase, we gave them the first representation of the energy level diagram that's classically shown. And here's an example of some things that we ask students. So we'll ask them about every feature within the representation. And here's some data where we're asking the students, what does that 0 mean at the top of the scale on the left-hand side? And you can see 3 students here. These are all pseudonyms. Students get to, my research students get to name them. So this particular student was in love with the Beatles. I can hear you laughing at my jokes, I know. Michael's laughing, so I can see that. Okay. Boy, I'm missing audience. All right. Paul says that 0 means no energy is required to get there. John says that's the ground state and it has no energy. And George says 0 can only be approached as n increases. Well, George comes the closest to being accurate and yet not really understanding what's in this diagram at all. So we talk students through what meanings they think are encoded here. Why do chemists use these diagrams? And so this is an example of the kind of data we would generate in our interviews. And then in the next phase of the interview, we gave the students 4 different representations of the helium atom in order to explore their thinking about probability. And we just recently published This was one of Michael's first papers as editor, I believe, in SERP. We just recently published a summary if you'd like to know more detailed descriptions about students' interpretations of those 4 representations. This paper summarizes our qualitative findings. And then we gave them some additional representations, this time for the carbon atom. And we gave them 2 different sets and talked them through which orbitals they thought they needed and why to represent the carbon. And then at the end, we explore connections amongst all of those representations. So these interviews typically take about 45 to 60 minutes to conduct these. And then from the analysis of students' thinking in those interviews, we turn those into multiple choice items. In this case, we created an instrument called the QPRI, the Quantization and Probability Representations Inventory. There are 23 items plus 3 preference items on here. And of the 23 multiple choice items, 3 of them ask students to reason with Bohr models, 9 with probability representations, and 8 with energy quantization representations. And there are some items that don't have representations. That's how we get to 23. And then I'll show you what we mean by preference items. This was a new kind of item for us to write. And the multiple choice items are intended to have 1 right answer. We run those through validity checks with faculty experts and response process interviews to make sure that students are selecting the right answer for the right reason. And the wrong answers on these come from the students' interviews themselves, right? So if you're familiar with David Tregus' work, where the faculty outline for developing instruments, where the faculty outline all the propositional knowledge statements and generate the distractors for those items, our work, instead of from top down, goes bottom up. We start with the students' thinking, and every wrong answer on our inventory can be traced back to multiple students' remarks during these semi-structured interviews that we have conducted. We also measure students' confidence about their thinking. We pilot test these here locally and conduct response process validation interviews, and then we send them out and turn them loose on the world. So in a former life, I was an analytical chemist, and this is my mindset here. We do method development, we show it works with a system of interest, and then we turn it loose to other people to use. So these are the representations that ended up on the QPRI that we asked students to interpret for us. So let me show you some data there. Our sample has 655 GC is general chemistry or first year university chemistry. And you can see out of a score of 23 that it's a hard instrument for students to respond to, especially as a reminder, this is after they've been taught and tested. This is as good as it's going to get for these first year university students. They average between 10 and 11 items correctly. And for the physical biophysical chemistry sample, which is 38 students total, you can see they answer about 5 questions higher. There's not a floor or a ceiling effect where we see all the scores crammed at either the extreme on the scale. But optimistically, I think we might expect juniors and seniors who have completed physical chemistry to score even better than what we have here. These people are about to set off to professional degrees in graduate school, and there's still some room for improvement in their thinking about energy quantization and probability. As I indicated, we asked students to indicate how confident they are about their answer. If there's a 2-tier question, we also ask them to tell us how confident they are about the reason. Some people like to do this with Likert scales, but then there becomes problems with running stats on a Likert scale. And so we have turned this into a number scale, and we ask students to mark it. And yes, I make my graduate students measure with a ruler where the center of the X is, and that's how we generate. It's their favorite task, I know. Okay, so let me remind you once again, this is what students know. And on the next slide, I'm going to show you what they think they know. That is how confident they are, the average confidence per student. This is what they know. This is what they think they know. So I'll just go back and forth there for a second. And you can see that the students are overconfident. In other words, they're not able to judge accurately the differences between what they know and do not know. So this goes towards the existence of the Dunning-Kruger effect. This has been found by many people who are studying projects in chemistry education. If I show you a scatter plot of how students do on items that had a probability representation versus an item that had a energy quantization. On slides, the first year university, which we've coded as Gen Chem, will be in blue, and the physical chemistry is always on the right-hand side in gray. And so you can see there's a range there. I've drawn in red lines at the mean for the number of probability and energy quantization items, right? And you can see that that distribution shifts for the PChem and biophysical chemistry, right? So this is evidence for concurrent validity. We would expect the PChem students to do better, and we do see that. I would like to point out, okay, Michael says there's a pointer. Let me try this. I got a shape. No, that didn't work. Oh, here we go. This row of data down here in the first year university chemistry on the left is very interesting. That you can see we have students who range from knowing nothing about probability to doing quite well with probability representations and still struggle immensely with energy quantization. So there's quite a spread here in the student data. Because we are making measurements tools, we worry about the ability of our instrument to discriminate among students and how items perform in terms of their difficulty. And you can see we have several items that are quite difficult over here in the lower left quadrant. Well, I guess it's not really a quadrant, there's 6 of them. You know what I mean, the lower left corner of the difficulty plot. And that doesn't mean those items are performing poorly, it just means that very few students got them right, which is also why they have lower discrimination, because they're equally difficult for the students who do very well as they are for the students who do very poor. So that's in first year university chemistry. And here's what it looks like for physical chemistry. And you can see sort of a shift in the difficulty a little bit to the right of the spread of the dots there, which again goes towards that we would expect PChem students to perform better on this. When we look at how students' confidence marries against their score, this is what the distribution looks like for Gen Chem versus PChem. This creates interesting thoughts for implications for the classroom, because when you have students in the upper right quadrant up here for general chemistry, these students know more and they're more confident. They seem reasonably well calibrated. Students down here in the lower left corner do not know as much and their confidence is lower. Again, they seem reasonably well calibrated. It's this group of students up here in the upper left corner that I really need to think about as a teacher in the classroom. They have the confidence of the better performing students when they perhaps should not have that confidence. Their confidence should be more calibrated with that of the students who perform with fewer successful items. And so there are different groups of students in our classroom, and they're all going to need different pedagogical responses here. You can see in the juniors and seniors that their average confidence is much higher, even though we have a spread of scores, right? So we have students who are on average about 60 to 70% confident in their remarks, who range anywhere from getting 7 items right all the way out to 19. And then I wanted to show you the preference items that we asked, because these are different than multiple choice with a correct answer. So we asked the students, you might recognize these as the 4 representations we gave them during the interview, and we say, which representation comes to mind when you think of the helium atom? And we asked them to indicate that. And so here's what the students in first year university chemistry told us. When they think of the helium atom, overwhelmingly, they picture representation D, 2 protons, 2 neutrons, 2 electrons, in a very classical Bohr model. Then we asked them which one they thought was most accurate. And this question comes from our interviews, where when we asked students to talk through these representations, multiple students in the interviews started saying things to us along the lines of, do you want me to tell you what I really think, or what my instructor said the right answer was? Right? And so that is very telling. We're certainly not the first people to hear that. If you ever had the opportunity to hear Eric Mazur talk, he talks about how his students say the same thing about the force concept inventory. And of course, we told our students, we want to know what you really think. And so now I'm going to show you the data for how they answered this when they took the Q-Pre. So when we look at this spread of data, this tells us that students really aren't sure which one is the most accurate. They know which one comes to their mind most readily, but they're not sure. This is for over 655 students who finished a first semester of university chemistry. They can't decipher whether one of these is more accurate than the other. So of course we asked the same question to the PChem students. Hopefully by now you're trying to predict what my data looks like in your own head. What would your students say they think is the, which representation comes to mind? Is it the same when you're a junior or senior, or different than first year? Got an answer in your head? This is what the juniors and seniors say. So they have a split between the classical model and representation A. And of course, to be fair, we're not providing a context for the students to reason in these. So we don't actually mark one of these as a right answer. We're interested in exploring that space between what students think and what they think their professors think. And so then we ask them which one is the most accurate. Get your prediction? I'm looking at you, Michael. Do you have a prediction? You're the only face I can see. Okay. So we have a large number of students who tell us that they think about it one way, but they think of the other one as being more accurate, right? And so students have these different mental models in their head, which points to when we ask them for a task, to reason through a task, how do we signal to them which mental model they should invoke? How do they decide which mental model to invoke? And then I'll just give you a few examples of items on the inventory, and then I'll stop for questions here about halfway through. One of the questions we ask students is, well, in this representation, just what are all those dots around here? And again, there is a right answer here to this item, and there are 3 wrong answers, and the 3 wrong answers all come from our interviews because this is the meaning students attach to them. And here's what the data looks like for this. Each dot, as you know, suggests a probable location of an electron, but we still have students who think of all these dots in the middle as being the nucleus, not about being electrons, but about being protons and neutrons. We asked them to talk us through some of the features of the energy level diagram here, and we asked them, well, what can it be used to explain? This comes from when would a chemist use this? And you can see here that we have ideas ranging from a hydrogen atom gaining electrons to heat being released to changing the energy of the atom, or that we're changing and breaking bonds. And so here's what the data looks like for both the first year university in blue on the left and the physical chemistry in gray on the right. Okay, so some students think that there's gaining electrons happening in this diagram. When we ask students what kind of energy is on this axis, the general chemistry students are really unsure. We have quite a spread. The physical chemistry students do better. I particularly love this question because as I've given this talk at conferences and universities throughout the States and Canada, this question causes disconsternation amongst the faculty. This is the point where physical chemists start arguing with each other about, no, that's not really just potential energy. The Hamiltonian has both potential and kinetic. What is it really on there? My point here is not to arbitrate fights amongst physical chemists. I would like to point out that this representation is very common in textbooks. We don't tell students what kind of energy it is. And in the absence of us teaching students how we would like them to decode the meanings in our representations, they will supplant their own ideas. And when we ask them why they chose their answer to that, you can see that we want them to think about the attraction between electron and a proton, but they're also thinking about breaking and making bonds. They think it's the energy within an electron. They're really not sure what this energy is that we are measuring with this diagram, which is ubiquitous when we introduce the quantum model. We ask them to compare representations. Are these showing related concepts or not? And when the students answer this, we have a lot who say yes because they both show energy levels. When they look at the representation here on the right, figure B, they see that as energy levels, n equals 1, n equals 2. All right. Okay, so I'm going to pause. Michael asked me to pause about halfway through before I move on to the second tool that we've most recently developed.
Great, thank you very much. This issue about knowledge confidence, you mentioned that this comes after a student's assessment. Do you think misplaced confidence might be because students actually did well on an assessment on this topic?
Sure, that's a great question. What is it that leads to their competence? So they're making some judgment about the accuracy of their knowledge. And so we don't have grade information to draw that correlation. I don't have human subjects approval to get a student's grade in the course to compare it there, but you might imagine or you might speculate that students who've earned higher grades would have no reason to guess that their knowledge is incorrect or inadequate or missing or has misconnected resources. It goes to the nature of the assessments they were given in those courses to earn those grades in the first place, right? If those courses are not asking them to do these tasks with representations, and this is the first time they're doing it, they're not aware that perhaps they're engaging in new tasks and appropriately thinking, perhaps I should be less confident.
Yeah, okay. And Nicole asks, do you have any thoughts about how much students' preferred mental image of the atom might change if they were given a context? So, such as in the context of differentiating elements. Sorry, I hope I'm representing that.
Yeah, that's a super question, right? So if we ask them to reason through atomic emission, which model would they pick and why, right? Which one is there? So there, the question is not which one is more accurate, but which one is more useful.
Yeah.
And which ones are less useful, and what features are they attending to? So those would be great follow-up studies to do with this work for sure.
Yeah, and I think just on that, I think I remember this from the paper at the time, but the images you show are effectively mimics of the images that are in textbooks. Is that right? Or
correct?
Yes. Yeah.
Correct.
Elena, it's at the Moon Group. So yes, you were showing the Gen Chems and then the physical chemists with the biophysical chemists. She just asks, I think it's more of a methodological issue. Can you explain your reasoning for pooling biophysical and physical chemistry students? Do you have evidence that they're comparable?
Sure.
Yeah.
We do. So both in the interviews, we didn't hear any different answers from them, and on the quantitative information, we did examine whether they were equivalent groups and whether we could pool their data. So yes, we do have that. I should say that the paper for the QPRE and the paper for the next one I'm going to talk about here with Tim's work, both of them have been revised and resubmitted. So fingers crossed, hopefully we will have papers forthcoming soon on both of those, and that data would be in there.
And I think I can squeeze in one more, which is Michael's. How do students reason about accuracy in the context of quantum mechanics or quantum chemistry?
An excellent question.
You said you're an analytical chemist at heart, so.
Right. And so you might think some of it, this is really interesting because even the experts don't challenge us about this. They will say which one they think is more accurate, but they really ought to be challenging the premise of the question itself, right? That when we think about the quantum model of the atom, we craft these representations as our best estimate of what it might look like if we were able to actually visualize it, but of course we can't, and there are limitations to our representations. And so even the experts don't push back on the limitations of the representations. They go straight to answering the question about this one's more accurate than that one.
Okay, great. If I haven't asked an audience question, please just bounce it in again, and I will pick up more questions towards the end. But for now, Stacey, please, if you can continue. Thank you.
Okay. So then the second one I wanted to share is the work that Tim did before he headed off to join Hannah Sevian's group at UMass Boston. And here we're looking at enthalpy and entropy with regard to dissolving and precipitating. And so here's are some of the representations we're looking at in this content area, right? So there's a lot of symbolic language here where we teach students to write balanced equations and memorize solubility rules and write net ionic equations, a lot of symbol manipulation. And we would like them to reason with the particle images and actually be able to connect that to the macroscopic, which in theory should be happening in the laboratory. So we wanted to show you some of our data there. There's been a lot of work done here that students before us, of course, students have been shown in many contexts to reason about ion molecules or ion pairs existing in solution. Students symbolically will indicate that compounds react with water because when you're manipulating symbols, you can move them around on the page however you want. But most of the work that was done before are forays into this area focused mostly on characterizing what a student thinks is happening and not the underlying driving forces or the why associated with enthalpy and entropy changes. And so that's where we wanted to situate our work. So we were interested in understanding when students observe that salt dissolves or does not, or a precipitation reaction has taken place, how did they explain the temperature changes that accompany that? To what extent, if any, do they invoke enthalpy or entropy arguments? How do they discuss spontaneity? These were the questions that we were interested in. And as in the previous study here, we use the same sequential mixed methods design. We still talk to students after they've been taught and tested. We also talk to students in first year university chemistry, as well as in our biophysical and physical chemistry courses. So the same design there. I won't spend much time on that. So here's what the interview guide looks like in the research that Tim and I did. After we talked with students about what they knew about enthalpy and entropy and the prior knowledge of the phase and why some things dissolve but not everything, we actually set them through 3 tasks. So in the last project I showed you, we were working more at the particulate and symbolic corners of Johnstone's triangle, and here we're invoking the macroscopic corner. And so we gave students magnesium chloride and asked them to dissolve it in a vial of water, and they were holding it and they could tell it got hot, and we asked them to explain that. And we gave them some silver chloride and some water and asked them to dissolve it, which of course it did not, and we asked them to talk us through why that was. Then we gave them some silver nitrate and some more water and asked them to dissolve that, and it gets cold when you feel that. And so now they have 2 solutions, of a solution of magnesium chloride and an aqueous solution of silver nitrate, and we asked them to pour those 2 solutions together, and of course that forms silver chloride, and we asked them to explain what was happening there. So that's the general overview of his interview guide. We should note that there are some limitations or boundary conditions, if you will, to this research. We only looked at water as a solvent. We only used ionic salts, so nothing molecular like sugar. We only did this at room temperature, so we were not looking at temperature effects on solubility. And we did not intentionally explore the space of KSP or equilibrium in the interview. A few students brought that up, but that is not, and if a student brings it up, we will go where they lead us, but we were not intentionally exploring that. So these are limitations or boundary conditions that really should be explored in future research. So we've published the qualitative findings of this research. First, how students explained the temperature changes, and we had 3 different groups of students there, how they explained why some things got hot and cold. And then we recently published a paper about the entropy and spontaneity thinking of students as well. So you can find both of those in JChem Ed. And I wanted to give you a sense of what they said. So in the prior knowledge phase, before we've given them any of those tasks, when we asked them about entropy, this is what we heard from Lupita, who's a physical chemistry student. So we see here the disordered chaos metaphors that are quite common, not only as for students of chemistry, but still among teachers of chemistry who invoke these metaphors, again, without discussing the limitations of these as teaching devices. When we were talking about spontaneity, Doug told us, well, if it just disappears, it's not spontaneous, right? And so you can see how when you ask a student something in the prior knowledge phase, methodologically, this sets up great conversation that can happen later, because Doug's about to dissolve 2 salts that are going to disappear. And now we get to ask him whether that was spontaneous or not, because he's told us here in the prior knowledge phase that if something just disappears, it's not spontaneous. And here's how he explained in phase 2 for the magnesium chloride. So Doug has some cognitive dissonance here, and Tim, as the researcher, gets to go in and explain, but you said earlier this, and see how the student is able to reason through the conflict in their thinking. Conrad's a physical chemistry student, and this was his explanation for why the magnesium chloride dissolving got hot. The well-known idea among students that when a bond breaks, it releases energy. And so Conrad, as a physical chemistry student here, is invoking that argument to explain the magnesium chloride solution being hot as he held it. But Conrad had to hold a silver nitrate vial just a little bit later, and it got cold. So what did he say then? I'll let you read that. So here he's arguing just the opposite, that breaking the bonds is not going to release energy, but actually required energy. And he himself points that out, and he's perfectly fine with that idea. So for some students, despite our attempt to set up cognitive dissonance, they saw this as not conflicting information. There's just differences in the bonds. Some bonds do this, some bonds do that. So they have fundamentally flawed ideas about the nature of bonds in terms of electrostatics. Some students tried to reason it using symbols to explain what was going on. So they wrote this equation where we see the known thinking of students where they're going to show it reacting with water, right? So they think of water as H plus and hydroxide ions, and now they're going to react those out and write a balanced equation. And if the equation is balanced, that must be correct. So they're invoking skills they've learned and have been tested on, and that constitutes an explanation for them. So Alex is saying that he doesn't remember his hydroxide solubility rules. He knows a strong acid would fully dissociate, but he's perfectly fine with writing it as a product anyways. So there's conflict here between students being able to actually offer an explanation for why the reaction is happening, what the driving forces are, versus just describing it in terms of symbols. And for many students, these symbolic representations suffice as explanations. They don't see them as just descriptions. They actually see them as having explanatory power. So we took all we heard in those interviews, and as before, we turned them into multiple choice items with students' explanations as the distractors. And so we call this the E2 DPI, the enthalpy and entropy in dissolution and precipitation. And we collected data post-assessment, post-instruction in the course. And here are a sample of first-year university students. It's still in blue on the left, but it's a different sample of students, so now it's 383. And you can see out of 28 items, on average, they scored about 12. The PChem data was about 4 items more correct, but still quite a spread for these 53 physical chemistry, biophysical chemistry students. Still, I think we would hope that they would do better. We looked at the item difficulty for both general chemistry and the physical chemistry, and you can see that the items highly discriminate with the more experienced students. Evidence there for the concurrent validity. And this is what their confidence distribution looks like. Okay. I want to show you something different with this project that we did. Oh, wrong slide. I forgot what order I had the slides in. Okay, it's coming. It's coming. It's after this slide. Okay, so if we map a scatter plot out of score versus confidence, you can again see different groupings of students emerging that you might respond to differently in the classroom. And for the physical chemistry students here, I've drawn the lines at 50% confidence and a 50% score. And you can see that almost all the PChem students are above 50% confidence, right? They're reasonably confident about their knowledge here. We wanted to make sure that students were using the confidence. I know this graph may be horrifying at first to look at, but I will talk you through this. We've never seen one of these published, so we're going to set out to try to do this here. One of the concerns we have is, do students use the full confidence range when they're telling us how confident they are? And so what we've done here is we've taken all the students and we've ordered them from left to right, from lowest mean confidence per student to highest mean confidence per student. So that's the red. And then for each of those students, we indicated their median confidence and as well as their minimum value and the maximum value that they used. In other words, the range, right? So if students were not using the scale efficiently, those blue dots ought to be collapsed on that red line. And so I don't have a way to quantify how well we think that scale is working, but we think a plot like this gives us some insight into the idea that students are in fact answering different confidence for different items. They're using the range. They're not just picking the number 25 and marking it all the time. And it's a little more noisy here for the PChem students, but this is what that same plot looks like for them as well. And so Surprisingly, even for the PChem students, you still see a wide range in their maximum and minimum confidence. Okay, so here are some items on there. The entire inventory has no symbolic equations, so no delta G equals delta H minus T delta S on this anywhere. But that's what this question is asking, right? Which one describes a reaction that's spontaneous at all temperatures? And we labeled it change in enthalpy, change in entropy. Here's the first year university data with almost 60% of the students getting it correct. The PChem data is over 3/4 of the students getting correct. That seems reasonably good. We'd like it to be all of the PChem students. But then we asked them this question. If you mix two aqueous solutions, which was the task at the end of the interview, right? They had made two aqueous solutions, now we asked them to mix to form a precipitate. So this question comes from that task in the interview. We tell them they mix it, they spontaneously reacted to form a solid. This caused a decrease in the entropy of the system, and we asked the students, how did the enthalpy change? Well, there's only three possibilities. The enthalpy went up, went down, or there's not enough information to answer. The first year university students do not have a strong showing here. How about the PChem students? This was really, I see Michael shaking his head. No, this is really, sorry, did I out you? Can everybody see you? I forget. Everybody can see you when we're on this, right? This was really concerning to us that these students who are juniors and seniors about to finish their degrees in chemistry do not think there's enough information to answer this question. 3/4 of them just got the previous question right about the verbal answer that parallels delta G equals delta H minus T delta S, but they can't reason in this context to tell us this. And when we ask them why, what answer best explains their answer to the previous question, the general chemistry students, this is essentially random guessing. Some of them think you have to compare breaking attractions between the water versus forming the bonds. Some think forming the bonds required energy to be input. Some think you have to measure the temperature, right? So if I go back to the previous question, we've told them something about spontaneity. We've told them something about entropy. We're asking them about enthalpy. So some of them are reasoning, well, I need to know temperature before I can tell you enthalpy, because from a symbolic equation point of view, they would like us to identify all the variables except one. So that's the Gen Chem data. You have the PChem data in your head? So this is really very concerning, right? They're not thinking about this in terms of formation of bonds and connecting that to the enthalpy and ultimately to the spontaneity. We asked them a question where they got a 50-50 shot. You dissolve a solid, the enthalpy increases. Should you feel it get hot or cold? We're asking them the interview task, right? To predict what they should feel. Here's the Gen Chem first year university response. It's not much different than 50-50. Do you have a prediction? Do the PChem students do better? What do you think, Michael? Are they going to do better? Michael said no, he's not that optimistic. The PChem students do not do better. 50-50. We tell them this time you dissolved a salt and it got warmer. Can you explain why it got warmer? So now we're not asking them to predict the temperature change, we're asking them to explain. And they have to compare which attractions are breaking and forming and the energy changes that go along with that. The correct answer here is D. And this is how the first year university students do, and this is how the physical chemistry students do. So I think this data is pretty surprising to most chemists because this is not a complicated organic reaction, not a complicated polymeric reaction, not a complicated biochemical synthesis. This is dissolving ionic salt in water, and students are lacking the fundamental understanding of the connection between bonds and energies here. We asked them the reverse question about it gets colder, which explains why this would happen and a beaker got colder. The Gen Chem students did a little better here than the warmer one, and the PChem students do better here. So there's something about this, things getting warmer and that misconception of bonds breaking, releasing energy that just continues to plague students. This was very interesting to us because in the interviews we heard something that we had never thought about, and that has to do with the idea of entropy being transferred. So if you look there at B, it says entropy was transferred from the system to the surroundings, and that explains why the entropy in the surroundings went up. They're thinking of entropy being transferred. Okay, and even a third of our physical chemistry students were still thinking about that. All right, I'm looking at the clock here. So, oh good, I'm on my last slide. So what are some conclusions we draw across these two projects? Students still tend to prefer reasoning with the concrete particle model of protons, neutrons, and electrons over the quantum model. They struggle to connect that quantum model to probability quantum model to probability representations. Students will change their ideas about enthalpy in a different context. They do not have one concept about enthalpy that they reason with across contexts. They can recognize changes in entropy, but they're challenged to reason about spontaneity without mathematical symbols and think about entropy and enthalpy. So I think some conclusions of our work methodologically is that using these representations in different domains are very powerful interview tools because you're trying to get students to move from describing to explaining. They have difficulty making connections there, and they're not aware of what they don't know. So the implications for teaching here are that faculty really need to learn that students can't decode. We think they're beautiful. We open up a book or paper, we fall in love with the representations, but we're not explicitly teaching students how to decode, interpret, and compare representations. Why do we use this one in this context, but this one in a different context? And that's what we need to do. I have several examples of how we can do that, but I think I'm just going to skip ahead to the end because I'm looking at the clock. These are other two. Yeah, sorry. I hate when people do that. I know, but I'm in charge of the clicker. There we go. I just wanted to get to my acknowledgement slide. And I want to thank Anna as the person who did the flame test work originally. And there's Tim and Zai and me on their graduation day. And I need to thank all the students who spoke with us about how they picture and model chemistry in their head, the faculty who shared with us their views about teaching, and the National Science Foundation for their generous support, and you for your attention. So I'll stop there and answer more questions.
All right, thank you very much. My heart is racing at those physical chemistry answers. I had two questions that just come to mind. One is, could you just, I think you're making it sound beautifully easy, this process of going from interviews to coming up with these concept questions. I mean, I imagine there's an awful lot of noise in those interviews as well. How do you kind of work through the data from a sort of a methods point of view to actually pick out what ends up as a concept question? I mean, do you sort of see things repeating again and again with students, or is it something that's flagged up in a misconception that's being published? How do you actually decide these are the 28 questions I'm going to have in my inventory?
Yeah, that's a great question. And students who are in my research group in the second year often have this idea that I have a preconceived inventory sitting in my head and I'm just waiting for them to figure it out. There are lots of iterations. So what we do is we conduct all the interview. We do a pilot phase of the interview to make sure that our questions in the interview guide are getting the students to talk about the things we want them to talk about. So that phase takes a whole year. That's year 2 of a graduate student's life. Year 3 is conducting somewhere between 3 and 4 dozen more interviews until we feel like we're saturated in the data set. We're not hearing anything new.
Okay.
And then we use constant comparative analysis between students, within the student, to the literature to identify themes that are reoccurring. And then we write as many items as we can. So sometimes that might mean in this 28 item inventory that I showed you, we started out with more than 50 items. And some of them duplicate one another. Sometimes, this is the painful part for a graduate student. Sometimes their advisor and me will look at them and go, we're gonna not ask questions about this part and we're gonna create a focus. And we're only gonna ask about this part. And they're like, but my data, I had all these questions I created over here that I lovingly birthed and, and created, and they're great questions, but they never see the light of day because you can't ask a student to answer 50 questions. And when it comes time to getting access for students to answer this, the way that we do this is we go into our laboratory courses, and we like to be out in the first 10 to 15 minutes of the lab period, so that we're not taking, labs have almost 100% attendance, lectures don't. We don't take very much time out of the laboratory period. They can still accomplish the laboratory experiment. And so there's this negotiation between having a focus for the inventory, how long will it take students to answer it, and that plays out a little bit differently in the life of each graduate student, or in the case of my postdoc now, who's doing one on reaction coordinate diagrams. Each one's a little bit different.
Yeah. Okay, there's a million questions, so I'll try and be as efficient as possible. So, Michael, what recommendations do you have for leveraging the Bohr model in the curriculum for learning about quantum models? So, in other words, students who come to us with the Bohr model,
right.
how do we use that in progressing towards quantum models?
Right. So my recommendations there are that it's really important to tie to the context that we're doing. Telling students what they've learned from high school or secondary school is wrong is not productive, because that leads to them setting up these, well, this is how I really think about it, but this is the correct answer in my class. I'm going to give the right response in this class, even though that's not how I really think about it. So my recommendation there is helping students understand the limitations, helping them understand that it works for one and only one element in the periodic table. And after that, there are limitations to what we can do and why people create models in the first place, right? So stepping back and talking about meta modeling, which Nicole Becker's been doing great work with lately, helping understand why do scientists have to have multiple models in the first place? The idea that there's not just one best model, but we will invoke different models at different times, is really important in getting students to work with these. I don't have data on that kind of teaching makes a difference. It takes us 5 years in the life of a graduate student to make one of these tools, and then the next step is to go out and make changes in curriculum and pedagogy, and hopefully these tools will be available for people to measure those kinds of changes in thinking.
Yeah. Kind of related in a way, Nicole, I think, is asking about the dissonance that students express in these interviews. Is there a teaching implication there? So she's saying, could you see that students are getting instructed in your interviews using cognitive dissonance and actually draw a teaching implication from this approach?
Sure. So I'm going to go back to some slides I skipped over here that show you things I use in teaching. So when I'm talking about how do students learn to do this, I'm going to show you some ways that I do this in my own classroom. So, and in the 2 textbooks that I've written. So here's a feature that's in our textbooks where we ask students to review their particle knowledge before they get started in a chapter, and then look for things that are they might answer as they're going to get going here. And so here are 3 representations we're going to ask students to work with, and we're asking them in this chapter, this is to figure out which of these are compounds are covalent and ionic, and what features do they attend to make that distinction, right? So students will say things like, I can't tell you because there's no formula. So I can't tell you because I can't decide from the formula if the 2 elements are both nonmetals or one's a metal and a nonmetal. So they have these symbolic reasoning patterns that they default to, and we're trying to scaffold them to, in the absence of symbols, meaning the periodic table symbols, there are other features of representations you can attend to, and we want you to look for those features when you're going through here. So setting them up to not always provide the formula or the name, and asking them to just reason with the symbols is good. Asking them, if I ask them, so here's a visual matrix that's we have in every chapter in our textbook that I'm an author on, and we ask them which molecule contains the most atoms. Instead of asking them one question about one representation, asking them these 6 questions about this matrix of representations is significantly more challenging, because some students might say A is the molecule that contains the most atoms simply because they see it has the most spheres, right? And so what do they attend to? They're counting spheres. Well, is that a molecule or not? Are those atoms or not? And so asking them questions about multiple representations where they have to decide they have to compare the representations is a higher order thing. And I've even taken to doing that on my exams by making questions like this. I can't photocopy exams in color. That's way too expensive. So these images will appear on my black and white multiple choice exams for hundreds of students at a time. But I will project these on the screen in my classroom, or if I'm running a simulation or an animation, so that the color, which is a key feature to pay attention to, is there. And students know that they're going to have to reason with these on the exam. And of course, that's the tail that wags the dog. I can't just teach and emphasize representations and then ask them questions that are all calculations. And so this is how I've gotten around, or the solution I've come up with to projecting this in my classroom. I can show you a different example for like a second semester situation.
Yeah, fantastic. And I forgot to say when introducing you, you have textbooks that have been written based on your research, which I think is just outstanding. Yeah. I'll keep going. We're over time, but I think there's just so many questions. I'll try and get a few more in. So Dawn asks, I think, something very useful, and I think I know the answer, but I'll let you say it. Do you have a database or a clearinghouse of all of these concept inventories that will be available for you?
Sure. Michael, if you can go back to my very first slide, because I would have to click all the way back there.
Let me just get there.
Sure. So on my website, which the URL is coming up here, there is a tab that says CER resources. So there's my website here at Miami, and there's a tab that says CER resources, and then there's a list of assessment. And it's a list of all the chemistry specific assessments that I know that have been developed with research data, not just the ones out of my group. Ours are listed there, of course, but everybody's assessments that I've tracked to, and they have links to the original research articles so you can find them.
Great, and I posted that in the chat area as well if people want to copy that link. Michael, yeah, so if we are able to access these inventories, what advice do you have for people using them in the classroom for teaching?
Well, I think there's no one best way to use them. I think I use them a lot for prior knowledge when I'm teaching first-year university students. So what knowledge are they bringing from secondary chemistry, right? So the things they know, I don't need to spend much time on. Sometimes they're very useful to convince students that they don't know all the things that they think they know. I have not used them in a pre-post fashion, but you could imagine doing that as well, like to show knowledge gains from where they start to where they end. If you're getting ready to make a change in pedagogy, maybe you're going to change from a traditional curriculum to an Adams-focused curriculum or the CLUE curriculum or something like that, and you'd like to have a cohort of baseline data to make a comparison to, that would be. If you're teaching physical chemistry, I think it would be really interesting to measure the prior knowledge these students bring with them.
Exactly what I'm thinking.
That remains, right? What is the knowledge network they're bringing to reason with all the calculus you're about to lay upon them?
Yeah. Sorry, Stacey, I'll just keep going. Stephanie, yeah, so you were using macroscopic representations. Do you think if you probe the PChem students in entropy, enthalpy with mathematical representations, would you see the same kind of cognitive dissonance? Or is that perhaps what they're leaning on?
Okay, so that's a fabulous question. And I know is Tim still on here? No, he left early. Well, I'll have to give him grief for that. Okay. I showed you that slide with the live scribe pen. So we have students who try to explain using calculus what's happening. And they will use equations that belong with isothermal processes to explain what's happening when the temperature, when the solution was exothermic or endothermic. They invoke all kinds of calculus to try to explain this. Most of it is not accurate. The paper that it was the second paper in the second half of the talk that's in JChemEd this January about dissolving and insolubility for entropy and spontaneity, that has some of their mathematical representations that they generate. So they know that they've learned a bunch of calculus, and they will try to use the math as an explanation. And indeed, math is a language. It can, at its deepest level, be an explanation. But for most of our students, it is more descriptive than explanatory, and they run into trouble trying to use the math.
Yeah, I will bring up that
Especially
paper.
with non-spontaneous things. They don't know what to do when they didn't see anything happen. Then they think, is delta G 0? Is it not 0? Was delta H and delta? We don't talk about when things don't happen. Yeah, that paper right there. Thank you, Michael.
Okay, I was going to say I'll finish, but there's one question who just come in, which I think is interesting, and I assume there's a few people perhaps I haven't been able to bounce their questions on just because it's been so busy, but I assume they will be able to contact you if
of course.
Question.
Sure.
But Michael asked a very interesting methods question, which is, what have you found to be unproductive methods for uncovering student conceptions or developing inventories? Which, I guess we're leaning on your experience here a little.
Oh, really interesting. Unproductive methods.
So I guess you're talking out this idea of interviewing, get this kind of qualitative base, and then build which.
I think unproductive is interviewing them without the tasks. So if we just conduct the interviews like we do in the prior knowledge phase, where we ask them question, tell us your understanding of enthalpy or of entropy. If I put this solid in water and it dissolved, what would that mean? That without connecting it to the representation corners, students are good at, some of them are reasonably good at talking chemistry. But it is these tasks where we confront them with the temperature changes or the visual information where or the representations that they've seen in the textbook all the time, and nobody's ever stopped to ask them, where we point out that perhaps the phrases and the key vocabulary that they try to impress us with fall short, right? If you ask students to give you an example of an ionic compound and they only have to do that with a name or a formula, that's problematic. We've done interviews. This is a paper published in SERP back in, I think, 2013 or 14. Cindy Luxford's the first author on it, where we asked students, we gave them a bunch of modeling materials and asked them to create an ionic compound for us, and they did it. And then we said, okay, now you have to create another one, not with just different colors, but a different kind of representation. And the idea that we had challenged them to create a second model of something was almost too big of a stretch for many of our students, because they had only ever learned one prototypical model.
Yeah. All right. Stacey, we have squeezed more time out of you than I should have, but thank you very much for such a fascinating talk.
Oh, I want to say thank you to you and to the RSC CER group. I really appreciate that. And to everybody who hung around to the very end. I'll be at the, it looks like a lot of people stayed. I'll be at the Canadian conference the first week of June and the Gordon conference in the middle of June. So I'm sure I'll get a chance to see many of you there.
All right. So can I just say formally thank you very much. We really appreciate it. This recording will be available. I have a feeling it'll be well watched and used. So thank you for sharing your expertise and knowledge and some of the work from the very vast amount of literature you have on this topic. We really appreciate it. And I will formally sign off this, and then